So let's take a look here at the composition of diet as it relates to energetic needs as well as metabolic needs for the body, in which we have to remember that based off of what the body needs, we have four distinct macromolecules that we must consume: carbohydrates, abbreviated CHO, proteins or amino acids, abbreviated AA, lipids or fatty acids, which will be abbreviated FA, and nucleic acids, which will be abbreviated NA. Now, when we talk about the digestion and absorption of these individual macromolecules, we'll get a little bit more detail into how we break them down and get them into the body. But let's look at them in terms of what we need them for. And so the first thing we have to look at is the caloric content of our food stocks. This is what we are referencing when we talk about the caloric balance for energetic metabolism. And this is how much can I get from the various substances, in which carbohydrates and proteins or amino acids will provide about 4 kcal per mole or gram of the substance that we get. Lipids or fats will give us anywhere from 7 to 9 kcal per mole or gram. It's usually referenced as 9, but the reference there in terms of what we get from the food stocks will vary based off of what type of food stock we're actually getting, as well as what other processing we have to do in order to get those things into usable forms for the body. So proteins and amino acids actually have more stored energy within them than what the body can actually get. We also have to metabolize fats and proteins into distinct metabolites before we can actually use them. And so the amount of energy that we get is going to vary, and the amount of return we get for that energy will vary. So the first one we're going to look at here is carbohydrates. Carbohydrates is a simple chain of carbons, hydrogen, and oxygens. The ratio is typically 1 carbon to 2 hydrogens to 1 oxygen. However, this reference ratio will vary based off of the actual carbohydrate that we're looking at. It's used for a fuel source. It's used for structural integrity within the cells. It's used as building blocks for other macromolecules that we need. The typical reference that we get is from the Greek, and it's going to be saccharides. And so we will see things like monosaccharides and then disaccharides. Monosaccharides include things like glucose and fructose. Disaccharides include things like sucrose and lactose. And then we get to the complex carbohydrates. And these are things like glycogen, starch, cellulose. Now, dietarily, we don't usually talk about cellulose as being a carbohydrate that is necessary for metabolism. However, it is necessary for dietary functions, and this is what we get in terms of quote-unquote fiber. Now, if you look at general recommendations, it says that total consumption should be somewhere between 60% and less of total kcal per day. But as I mentioned earlier, we need to make sure we have somewhere around 120 grams of carbohydrates, in particular glucose, per day in order to maintain normal neurological functions. There are some reference values that we have where a healthy individual can consume somewhere between 2.5 and 3.5 grams per kilogram of body mass. Highly active individuals should be consuming about 0.8 grams of glucose per kilogram per hour of exercise to restore glycogen that might be depleted. Now, we don't necessarily have to be constantly consuming carbohydrates throughout the day, and we'll get more into that later on, in order to maintain carbohydrate levels at usable ranges. If we look at the very low carbohydrate diet research, we can very safely consume levels as low as 10 grams per day. And we can maintain body mass by consuming between 45 and 110 grams per day safely. Now, if you notice, these levels are much lower than what we would want in order to maintain normal neurological functions. But we have processes that take place within the liver that allow us to maintain our 120 grams of carbohydrates per day to maintain normal neurological functions. Additionally, neurons will utilize other fuel sources, which we'll talk about when we talk about ATP regenerations. Amino acids are larger molecules that contain a amine or an NH2 and a carboxyl, a COOH group, branching off what's referred to as a chiral or central carbon. Attached to the other end of this carbon is a group known as the R group. In the metabolism packet, I've given you a schematic of the various amino acids that we need. The R group is the functional group for the amino acid, and it makes each amino acid unique. When we talk about amino acids, we determine them based off of the dietary components, meaning do we need to consume them in order to have them available to us, or can we go about synthesizing them? If we cannot synthesize them, they are essential. If we can synthesize them, they become non-essential. The non-essential amino acids usually get made off of carbohydrates as their central backbone, and then get aminated during the amino acid synthesis processing. When we look at the R group, we talk about them based off of the general chemical shape in which they can be branched chain. That means that they have subunits that come off of the line of carbons within the R group. They can be polar, which means that there's the presence of a thiol group or a sulfide group, a SH group on it. The R group can be polar or nonpolar, meaning that there is no ability to form hydrogen bonds within the R chain. We can also look at them in terms of the metabolic action. That is, are they going to be glucogenic, meaning that they can provide the carbohydrates necessary to do gluconeogenesis, or are they ketogenic, meaning that will they break down to form ketone bodies, beta hydroxybutyrate and acetoacetone? When we talk about consumption, the consumption guidelines generally have somewhere between 10 and 15% of total energy demand based off of amino acids or proteins. This guideline, however, is a rough estimate. In fact, there's very little agreement in terms of what is actual bare minimum for protein consumption. It is dictated as being age and level of physical activity dependent, and that's because we need proteins in order to rebuild tissues that get broken down during activity, need tissues that are growing, such as what happens during growth, or need tissues that need to undergo constant rates of repair, which occurs as we age. The general range that is given is somewhere between about 0.8 to about 2.2, and we know that somewhere between 1.2 and 2.5 is good for people who have general level of physical activity. There is no benefit for anything higher than 2.5 grams per kilogram body mass. The people that stipulate there is benefit from having this excessive amount of proteins are ignoring what is coming from the exercise stimulus in terms of its hormonal response. For people who undergo high amounts of endurance activity, additional protein is necessary as protein gets oxidized and catabolized to meet ATP demands. For people who are attempting to lose body mass through diet, through caloric restriction in particular within the diet, you need to consume greater than 1.8 gram per kilogram of body mass, with the highest benefit or greatest efficiency coming at between 1.8 and 2.7 grams per kilogram body mass. This will ensure that loss is of fat mass and not of fat-free mass, bone, and muscle. When we talk about fatty acids, we usually talk about it in terms of energy, but the problem is that it goes much beyond energy. Lipids are necessary for membrane. Lipids are essential for hormones. It's not just about energy. So lipids are normally just a long chain of carbons and hydrogens with a carboxyl into it. The most common of them are the large triglyceride lipid droplets of palmitate and oleic acid. We're usually going to see them on a backbone of a glycerol molecule. If we have a phosphate attached to it, it becomes what's referred to as a phospholipid, and the phospholipid is what is used to form all of the membranes. So what's it going to be used for? Well, yes, it's going to be used for a fuel source. Yes, we can store it. In fact, we have a larger ability to store lipids than we have to store anything else. We can store about 600 grams of glycogen throughout our body. There seems to be no limit to the amount of lipids that we can store, however. They provide for protection via insulation, as well as act as a shock absorber. They are necessary for productions of hormones, such as steroid hormones. They provide insulation to neurons and provide for normal neurological functioning. The synthesis of lipids come from carbohydrate metabolisms that can accumulate within cells, as well as hormonal signals that will direct regulation of metabolism. When we look at the fatty acids, we typically have three distinct types of fatty acids that we talk about: triglycerides, cholesterols, and stanols. When we talk about triglycerides, we'll talk about them based off of the fatty acids that are attached to them, in which we have what are referred to as saturated fatty acids. This is where there are no double bonds within the molecule itself. Solid fats at room temperature are saturated fats. The monounsaturated fats have one double bond within them. These typically are liquid at room temperature, but will solidify as they become chilled. The last are the polyunsaturated. The polyunsaturated have multiple double bonds within them. The multiple double bonds are going to keep it from solidifying, which means that it will tend to always be liquid unless it is actually frozen. When we look at the fatty acids, there is another type of fatty acid, which is a synthetic fatty acid. These are referred to as hydrogenated or trans fats. The hydrogenated or trans fat is where we take an unsaturated fat and turn it into characteristically a saturated fat. The problem is that the way in which the bonds line up does not allow for the body to digest the fat down very easily and can act as saturated fats, which is why most of these fats have been quote unquote banned from food. Additionally, we have a couple of specialized lipids that we have to remember. One is the phospholipid. The phospholipid we talked about as relates to the cell membranes. But then we also have the cholesterol molecules. The cholesterol molecule is going to be the precursor for all of the steroid hormones. And without the cholesterol molecule, we do not get steroid hormones. This cholesterol molecule also acts as a membrane stabilizer, and the membrane stabilizer is essential to make sure that membranes stay intact. They will also be part of the lipopolyproteins, the HDLs, the LDLs, and the VLDLs. Now, even though we talk about HDL, LDL, and VLDLs as being quote unquote cholesterol, they are not the cholesterol molecule themselves. They are a cluster of fats and proteins that are being transported around to other areas of the body from the liver in vesicles that allow them to be transported within the bloodstream. Now, in terms of overall dietary component, the American Heart Association stipulates that we should have less than 25% of total caloric demand being met by fats. However, if we look at the ketotic diets, the diets that induce ketone development, increase of fatty acid oxidation will occur with increased lipid consumption, with the indication that you can safely consume up to about 50% of your total kcal per day being in fats. Along with this, we have breakdowns that we have to worry about in terms of consumption of fats, in terms of the polyunsaturated versus the saturated, where we want to make sure that we are consuming a higher proportion of our fats from the unsaturated fats than from the saturated fats, and that we should be consuming somewhere around a 2 to 1, 3 to 1 ratio of the polyunsaturated to the monounsaturated. But even then, the monounsaturated fats, we need to make sure that we get 2 essential fatty acids within our diet. And those 2 essential fatty acids within our diet are the omega, in particular the omega-3 and the omega-6. The omega-3 and the omega-6 fatty acids are essential for membrane building and are usually considered to be the quote-unquote healthy fats within the diet. We'll get more into that when we talk about some of the lipogenesis and lipolysis functions when we talk about the biochemistry stuff.